So the second derivative of a function is exactly that. We differentiate the derivative, yeah? But it's got a few different really nice graphing applications and information about a graph's stationary points, whether they're a maximum, minimum, or points of inflection. So if we just first of all look at the practicalities of finding our second derivative, it is, as you would expect, just differentiating a second time. So if we have a polynomial function, we find our derivatives, so we'll have 24x cubed minus 12x squared plus 4, differentiate a second time, 3 24s are 72, 2 12s are 24. So there's my derivative, or my second derivative there, all right? We'll talk about its applications a little bit more later. Here we have e to the x sine x, so we have a product, two distinct functions here, and e to the x and the sine x multiplying, so we know it's a product rule. So obviously derivative of the first, which is e to the x, times the second, plus derivative of the second, so the derivative of sine x is cos x, times the first. So there's my derivative function. So now if I want to differentiate e to the x sine x, well, from the previous example, it's just a repeat of the top. So now I need to differentiate the second function there with the red bracket. So the derivative of cos x e to the x is the derivative of the cos x, which is negative sine x, times the first, plus the derivative of the second e to the x times the first function cos x. So we'll have a quick look through that. We can see that we've got an e to the x sine x, a negative sine x e to the x, so they can cancel out. So that leaves me 2e to the x cos x. I guess we can check that there just on our cas dump. Using the cas, we can differentiate line by line, like I have in the first example. Or we can just take the derivative of and then insert the derivative a second time to get our second derivative straight away. All right. Example 7 there, we've got a function f double dash. So f dash of x, k e to the kx, so 2e to the 2x, differentiate a second time, k e to the kx, 4e to the 2x, if I want to substitute 0 into there, 4e to the 0 is 4 times 1, which is 4, which is what we have. Finally, we've got a little expression there that we want to sort of simplify and show and prove, or evaluate, simplify I should say. So if y equals cos 2x, derivative of cos 2x is negative 2 sine 2x. The derivative of negative 2 sine 2x, k comes out the front again. Derivative of sine is cos, so it's negative 4 cos 2x. So if I substitute those expressions in, so I guess if we substitute dy dx in, I get negative 2 sine 2x all squared, which is 4 sine squared 2x. If I substitute negative 4 cos 2x in for the second derivative and square that, I get 16, negative 4 squared, 16 cos squared 2x. A quarter of that out the front gives me a 4 cos squared 2x. Obviously the 4's are common, so if I take them out the front, I get a sine squared 2x plus cos squared 2x, which is 1. So the whole thing simplifies to 4, which is what our cas printout has given us. All right. So just initially, let's just look at the practicalities and the processes involved in determining our second derivatives.